In the vast silence of space, stars appear constant, stable, unchanging. But inside the most massive stars, stability is temporary. A star lives by balancing two forces. Gravity pulls inward. Nuclear fusion pushes outward. As long as fusion continues in the core, this balance holds. For stars far more massive than the Sun, fusion progresses through stages. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, neon, silicon. Each stage occurs faster than the last. The final product is iron. Iron is different. Fusing iron does not release energy. It consumes it. Once a massive star builds an iron core, fusion can no longer support it. Gravity wins. In less than a second, the core collapses inward at a significant fraction of the speed of light. Temperatures exceed billions of degrees. Electrons and protons merge under extreme pressure. Matter transforms. The core becomes something extraordinary. A neutron star. The collapsing core compresses to nuclear density. A teaspoon of neutron star material would weigh billions of tons. As the core collapses, it rebounds. The outer layers crash inward and then explode outward in a violent supernova. This explosion releases immense energy. For a brief period, the dying star can outshine an entire galaxy. Supernovae distribute heavy elements into interstellar space. Carbon, oxygen, silicon, the building blocks of planets and life. But something more extreme happens in these explosions. The environment becomes rich in neutrons. Under such conditions, atomic nuclei capture neutrons rapidly. This is known as the R process, rapid neutron capture. Supernovae were once believed to be the primary source of heavy elements beyond iron. But observations have revealed something even more powerful. What remains after the explosion is one of the densest objects in existence, a neutron star. It contains roughly the mass of the Sun compressed into a sphere only about 20 kilometers wide. Gravity at its surface is extreme. Magnetic fields can be trillions of times stronger than Earth's. Some neutron stars spin rapidly. These are pulsars, emitting beams of radiation like cosmic lighthouses. Others are magnetars, with magnetic fields so intense they distort atomic structure. But the story does not end with a single neutron star. In some binary systems, two massive stars evolve together. Each undergoes supernova. If the system survives both explosions, two neutron stars remain locked in orbit. And over millions of years, they spiral toward each other. Their orbit shrinks. Their speed increases. Their gravitational influence intensifies. Eventually they collide. Binary neutron star systems lose energy through gravitational radiation. As predicted by general relativity, accelerating masses emit gravitational waves. These waves carry energy away from the system. The orbit gradually decays. The stars spiral closer. In the final seconds before collision, they orbit hundreds of times per second. Space-time itself vibrates violently. The collision is not merely explosive. It is transformational. This event, known as a kilonova, releases enormous amounts of neutron-rich material. It is within these collisions that the heaviest elements in the universe are forged. Gold, platinum, uranium, the jewelry we wear, the metals and electronics, the rare elements in Earth's crust. They were not born in ordinary stars. They were born in the collision of neutron stars. But for decades this remained theoretical, until humanity developed instruments capable of detecting gravitational waves directly. And in 2017, one such collision was observed. For the first time, the origin of heavy elements could be confirmed. On August 17, 2017, a faint distortion passed through Earth. It was not visible. It was not audible. But it was measurable. Two detectors belonging to LIGO in the United States registered a signal. Moments later, the Virgo detector in Europe confirmed it. The signal lasted nearly 100 seconds. That duration was unusual. Previous detections had been short, fractions of a second, from black hole mergers. This signal was longer and lower in frequency. It carried a characteristic rising tone, a gravitational chirp. As the two objects spiraled inward, the frequency increased. The waveform matched predictions for a binary neutron star system. The event was designated GW170817. For the first time, humanity had directly detected two neutron stars colliding. But something even more remarkable followed. Just 1.7 seconds after the gravitational wave signal ended, a gamma-ray burst was detected by space-based observatories. That delay was crucial. It confirmed that gravitational waves travel at essentially the speed of light. Astronomers immediately began scanning the sky region identified by triangulation between detectors. Within hours, telescopes located a new point of light in the galaxy NGC 4993. This optical counterpart was a kilonova. For the first time in history, a cosmic event had been observed in both gravitational waves and electromagnetic radiation. This marked the beginning of multi-messenger astronomy. Gravitational waves revealed the mass and orbital dynamics. Light revealed the chemistry of the explosion. The kilonova spectrum showed signatures consistent with heavy element formation. Blue light initially dominated, then shifted to red over days. This evolution matched theoretical predictions of R-process nucleosynthesis. The theory that neutron star mergers produce heavy elements was no longer hypothetical. It had observational confirmation. During the merger, neutron-rich matter is ejected at high velocity. In this extreme environment, atomic nuclei rapidly capture neutrons. This is the R process. Rapid neutron capture creates unstable heavy nuclei. These nuclei then undergo radioactive decay into stable heavy elements: gold, platinum, rare earth elements. Spectroscopic analysis of the kilonova confirmed the presence of heavy elements consistent with R process production. Models estimate that a single neutron star merger can produce several Earth masses worth of gold. This gold disperses into interstellar space. Over millions of years, it becomes incorporated into new star systems, including ours. The gold in Earth's crust did not originate in the Sun. It predates the solar system. It was forged in a neutron star collision billions of years ago. When Earth formed, it inherited this cosmic debris. The origin of gold is astrophysical. It is gravitational. It is violent. The 2017 detection changed astrophysics permanently. Gravitational wave astronomy moved from theory to routine observation. Since then, additional neutron star mergers have been detected. Each detection refines mass estimates. Each improves models of heavy element formation. Instruments have been upgraded. Sensitivity increases yearly. Future detectors will detect events farther away and earlier in the inspiral phase. Ground-based observatories such as LIGO and Virgo continue improving. Next-generation detectors like the Einstein telescope are planned. The goal is precision. To measure how often neutron star mergers occur. To quantify their contribution to the cosmic abundance of heavy elements. To understand the population of compact objects across the universe. Gold is not rare because the universe cannot produce it. It is rare because the events that create it are rare. The cosmos does not produce gold gently. It produces it catastrophically. And we now have the instruments to witness it. When two neutron stars collide, the event is violent but brief. The merger lasts milliseconds. The kilonova glow persists for days. But the consequences last billions of years. The neutron-rich ejecta expand into interstellar space at enormous speeds. As this material cools, heavy elements form through radioactive decay. Gold nuclei stabilize. Platinum nuclei stabilize. These atoms do not remain clustered. They disperse. Interstellar turbulence spreads them across molecular clouds, vast regions of gas and dust where new stars are born. These clouds are not pristine hydrogen and helium. They are enriched by generations of stellar explosions and compact object mergers. Every new star inherits the chemical history of its environment. The solar system formed approximately 4.6 billion years ago inside one such enriched cloud. Within that cloud were trace amounts of heavy elements, including gold, forged long before the Sun existed. Gold on Earth is older than Earth itself. It is older than the Sun. Its origin lies in events that occurred in a different stellar generation. As gravity caused the molecular cloud to collapse, it formed a rotating disk around the young Sun. Within this protoplanetary disk, dust grains collided and stuck together. Over millions of years, these grains formed planetesimals, the building blocks of planets. Heavy elements were incorporated into these early solids. Gold atoms became embedded within rocky material. During Earth's formation, much of its early interior was molten. Heavy elements like gold are siderophiles. They prefer bonding with iron. As Earth differentiated, iron sank toward the core. Gold followed. Most of Earth's original gold likely resides deep within its core. The gold accessible in Earth's crust today may have arrived later. Late heavy bombardment by asteroids and meteorites delivered additional heavy elements to the surface. These impactors themselves contain material from ancient neutron star mergers. Thus, the gold we mine today is the product of multiple astrophysical processes: neutron star collision, interstellar mixing, star formation, planet formation, planetary differentiation, asteroid delivery, a chain spanning billions of years. The universe is not static. It recycles. Stars form from enriched material. Stars die and return heavier elements to space. Compact objects collide and add even heavier elements. Each generation increases chemical complexity. Without neutron star mergers, the universe would contain far fewer heavy elements beyond iron. Without heavy elements, rocky planets would be rare. Without rocky planets, surface chemistry leading to life would be unlikely. Gold is often viewed as a symbol of wealth. In astrophysical terms, it is a tracer. It traces extreme density, extreme gravity, extreme events. The abundance of heavy elements in a galaxy reflects its merger history. Galaxies with frequent compact object mergers will show different enrichment patterns. By studying elemental abundances in stars, astronomers reconstruct galactic evolution. The gold in Earth's crust is a record of ancient gravitational violence. It is not merely a metal. It is an archive. Every atom heavier than iron in your body has an origin beyond ordinary stars. Calcium in bones, iodine in blood, gold in electronics. These elements were formed in environments of extreme physics. Neutron stars represent matter at nuclear density. Their mergers represent some of the most energetic events since the Big Bang. When we measure gravitational waves from such collisions, we are not merely detecting distant noise. We are observing the process that created part of the material foundation of our planet: the ring on a finger, the circuitry in a satellite, the trace elements in Earth's crust. They began in a kilonova. Astrophysics does not merely describe distant phenomena. It explains origins. Neutron star collisions are not rare curiosities. They are essential chapters in cosmic chemical evolution. When two neutron stars merge, space-time vibrates. Heavy elements form. Interstellar space becomes enriched. Future planets inherit that material. Billions of years later, conscious observers study its source. The origin of gold is not terrestrial. It is gravitational. It is cosmic.